Good afternoon. My name is Tom Degnan. I am an emeritus professor from the University of Notre Dame, and it's my pleasure to introduce the first of the virtual member-led event for Section 3. The topic is carbon utilization infrastructure markets research and development, and this is a webinar that was organized by Jingwang Chen and with help by Jean Tom. A couple of protocol items. This webinar is going to be recorded, and we will be collecting questions and answers. The proper protocol for asking questions throughout this webinar is the little tab on the bottom that says Q&A next to the share button. It is not to raise your hand, not the raise hand or not the chat. So please, when entering questions, use that attribute for Zoom. We'll be taking questions throughout the panel, but won't be answering those until the end. So please don't expect your questions to be answered until the very end of this. And with that, let me then introduce and turn it over to Professor Jingwang Chen. Jingwang is the Thayer Lindsley Professor of Chemical Engineering at Columbia University. Jingwang?
Yeah, thank you, Tom. So to set up the meeting, the goal of the meeting is I'm showing this one graph that showing the CO2 concentration in the atmosphere. So this, you probably all seen this figure before, but by and large, this is summarizing over the last 800,000 years about the CO2 concentration, which you can see is over the last 800,000 years, the CO2 concentration by and large remain relatively stable. However, in the last 60, 70 years, you can start to see a very dramatic increase. Especially you can see the increase is not linear. So therefore, we have to consider mitigation approaches on how to reduce the CO2 in the atmosphere. And this is where the report came from National Academies of Sciences, Engineering, and Medicine. And this report was published in August 7, 2024, and we're going to be discussing today. So Tom, there's one more slide for you.
Thank you, Jingwang. And right after this, I'm going to introduce the rest of the panel members. But I think this is the second slide we wanted to use to highlight the case. And this shows really the projected CO2 emissions in the U.S. As we proceed. We've seen certainly over the last 2 decades a diminishment in the amount of CO2 that's being produced, but the projections are, and that's mainly as a result of the switch over from coal to natural gas. But the projections are that we're going to be seeing a leveling out of about 4 billion tons per year. Even in the lower economic growth case and low ZTC. So I think this is makes a compelling case for why we need to look at negative carbon emissions and really the basis for the presentation today. Let me also introduce then Professor Emily Carter from Princeton University, who led this study we're going to be talking about. Professor Joe Powell, who's retired from Shell Oil. He's currently at the University of Houston. And Professor Alyssa Park, who's currently Dean of Engineering of UCLA. Again, as we go through this, please raise questions using the question and answer tab. And at the end of this, we will try our best to address as many questions as we can. You can also vote on the questions. And if you see a duplicate or if you see one that resonates, please use that tab and you can actually comment so we can actually see the questions that raise the most amount of interest. So with that, Jingwang, I'll turn it back to you.
Yeah, Emily, please go ahead. Yeah.
Okay. Well, thank you. I appreciate everybody attending this webinar, and I just want to set up and give you a bit of an overview, both of the history of the study, as well as some of the main conclusions from our work. So this study originated, it was an act of Congress in 2020, and it was meant initially as a follow-up to the 2019 study done by the National Academies on gaseous carbon waste streams. However, that focused just on gaseous carbon, so CO2 and methane. The studies we're talking about actually don't focus on methane, but focus on CO2, but also with a look at other carbon waste streams, in particular coal waste, as I'll mention in a moment. This earlier study also was focused on understanding the status of utilization of carbon waste streams and the research needs to enhance such utilization. So very focused on research. The work that we have done over the last few years, finishing last in 2024, was first of all, the work was sponsored by several offices of the Department of Energy, Fossil Energy and Carbon Management, Energy Efficiency and Renewable Energy, and the Office of Science. The framing is much broader than the earlier study, not just R&D, but also looking at what is needed, the status of, and what is needed for infrastructure, what might be the markets, various societal issues and impacts focused on a net zero emissions future. The output of this study, we were mandated to produce 2 consensus reports. And the idea is that we were to help provide information that could inform decision-making about CO2 and coal waste utilization from the point of view of funders, planners, developers, and research communities in order to advance markets, infrastructure, science and engineering of carbon utilization technologies that are relevant for a circular carbon economy. These are the cover pages of the 2 reports. I'm going to spend just a couple of minutes explaining the context and also some highlights associated with what came out of the reports. Obviously, you can go read in more detail the nature of the conclusions. So the first report, let me hide this, there we go. The first report, in terms of highlights, one of the main insights that came out of that first report is recognizing that where the CO2 comes from, the source of it, and what kinds of products are consistent with a circular carbon economy or a net zero future, we have to think about that very carefully in terms of how to pair sources and products. And then there were also issues with respect to what might be optimal infrastructure developments and also quicker wins that could be done in this space of CO2 utilization. So with respect to that, with respect to the source product pairing, if you think about fossil source CO2, for example, from power plants, the only thing that is net zero emission compatible would be long-lived products. Any fossil CO2 to short-lived products just delays the emissions because eventually those products decay and reproduce the CO2. And so that's not obviously not net zero emission compatible. On the other hand, having CO2 that comes, for example, from direct air capture or direct ocean capture or from biogenic sources of CO2, such as bioethanol plants, one can use those sources together with hydrogen and renewable electricity and water to produce either long-lived products that give rise to net negative emissions or short-lived products that at least are net zero emissions compatible. So what we know is that certainly fuel molecules, such as fuels and chemicals, are short-lived. And so they must come from direct air capture, direct ocean capture, or biogenic CO2 to be compatible with a net zero future. So this source dependency is very important to analyze, and it requires a full life cycle analysis in order to understand whether or not we can actually make this work. From the infrastructure perspective, co-location of infrastructure, for example, the production of hydrogen and the capture of CO2, should be thought about as potentially building it out in the same place so that one can avoid the transport of various ingredients. In addition, the possible coupling or piggybacking of carbon utilization onto planned infrastructure for carbon capture and storage would reduce the cost. Finally, in terms of quick wins, the committee found that producing jet fuel from bioethanol off gas and mineralization to aggregates that, for example, could be used for cement or road paving materials would be it is much closer to market than other applications using CO2 as a feedstock. The final report, which we turned to after that initial report, was to go further and deeper, but also broader, and understand the challenges in expanding infrastructure across the United States, mitigating environmental impacts. What are the challenges involved with those? Challenges involved with accessing capital, overcoming technical hurdles, and addressing all sorts of societal issues and geographic issues. In particular, Congress mandated that we should identify potential market opportunities. What are the greatest market opportunities for CO2 utilization, opportunities for support of small businesses, and examine infrastructure as it exists today and what is needed for the future, and the environmental impacts and economic and climate impacts associated with CO2 utilization. Assessing then the status of technologies for CO2 utilization, and then coming up with a comprehensive research agenda needed to really bring those technologies to the forefront. And then finally, as I mentioned earlier, also examining the feasibility and opportunities for commercializing coal waste derived products. We had a marvelous committee that spread over a wide range of expertises on CO2 and coal waste, both in terms of research, in terms of policy, in terms of techno-economic and life cycle analysis, and beyond. And they're all here, and I was really fortunate to work with them. The people shown in the gold squares are with us today. So what was the report structure of this report that was delivered in August of 2024? You can see it here. There were a number of chapters related to markets, policy, and infrastructure, and then an even larger number of chapters related to this comprehensive research agenda, crossing everything from solid materials to different kinds of molecules that we will need in the future. And out of that came a series of findings, 63 findings, 55 recommendations, and 71 research agenda items. I don't expect any one person will want to read the entire report. Maybe some of you will, but the report has been structured in such a way that you can go in and look at an individual chapter and learn what you need from an individual chapter. And there are many appendices for different audiences. So you may also look at the appendices and see particular appendices that are useful to you. With that, the context of this, again, is how do we address under-examined needs in a net zero future? And there are two themes, one having to do with durable carbon storage, how we can use CO2, for example, with minerals to make construction materials or to make solids of various kinds that are durable and will not decay. The other is the molecules, the carbon-based molecules that we need for chemicals and fuels, and that will be part of a circular carbon economy. And where will CO2 be advantaged or disadvantaged compared to other feedstocks? So if I look at, for example, very high-level highlights associated with market, technology assessment, and infrastructure findings and recommendations. In terms of the market, we have to think about always, will CO2, obviously carbon is always going to be with us. We need carbon-based products, but which ones are where CO2 might be advantaged? Given the amount of CO2 that we're talking about, ideally we're talking about producing materials or molecules that have high volume potential. And then recognizing that CO2 is, of course, the most oxygenated state of carbon, thinking about materials and molecules that are heavily oxygenated makes a lot of sense to use CO2 as a feedstock. So in particular, there are three different products classes that make sense. One is the high demand cases that have no zero carbon option. For example, jet fuel. For example, urea as a fertilizer, and a variety of different chemicals. Oxygenates and carbonates, for example, making concrete. Durable storage, again, inorganic carbonates, concrete, or solid carbon. From the from the technology assessment point of view, I've already mentioned life cycle assessment. It's also the case that we need to improve. One of the main things that came out in assessing the status of those right now is that there is a need to improve the evaluation of non-CO2 environmental impacts and circular carbon use processes. Finally, infrastructure. The current infrastructure we have for moving CO2 around is about 5,000 miles of pipeline, mostly in a region where it's used for enhanced oil recovery. It is not sufficient for what is needed for a CO2 utilization in a net zero future. In addition, we need to understand if we are to build out more pipelines in the future, which is still up in the air, we need to understand how to make sure they're safe. And both in terms of the engineering of the best pipelines for transporting CO2 and the policies needed for safety. And I'll just highlight that the lower right is a picture of a crater that was formed in a pipeline rupture. So with that, I will turn it over to my colleague, Joe Powell.
All righty. Well, thank you, Emily. I'm Joe Powell. And first, I'd like to thank Emily for 3 years of leadership on this committee, working together on more than 850 pages of reports. It really is an esteemed committee, and was very honored to be part of it. And also to Jing Wang for helping with this particular segment, which is chemical CO2 conversion to hydrocarbon products and materials and fuels. And so as Emily mentioned, these are the underpinnings of the current hydrocarbon economy. We'll look a little bit more at short-lived and really what is that. So you think about polyethylene going into a landfill that may have a life of 1,000 years if no one touches the landfill. But the point is, more and more of that material is getting incinerated to power and also incorporated into a circular economy. It's also mixed with biomass and other renewable components, and hence has to be looked at it in a systems way to be processed. And hence really are looking at what comes back at you in a relatively short life and in a future circular economy, as well as the incineration that's going on today. So this segment will look at hydrocarbon fuels and chemicals made from CO2. And that CO2 requires a lot of energy and hydrogen to bring it back into the reduced molecules that we need for these fuels and chemical performance products. And so one must keep in mind that amount of energy and or hydrogen that needs to come into play and what the source is in terms of making these products. You see in the second block here, the different processes. We'll talk about thermochemical, electrochemical, photo, plasma options, and then integrated capture and conversion as the mechanisms, along with combinations of all of these in terms of pathways. We also have single carbon products and then multiple carbon products with carbon-carbon bonds. And that's where it gets a little bit more difficult to compete with petroleum, which already comes with carbon-carbon bonds. And we'll look at the opportunity space for making that from CO2. Another thing to keep in mind is a lot of our products today are reduced hydrocarbons. The really good opportunities in the CO2 space quite often come in terms of making oxygenated products. So if you're looking at the polyols or also looking at some of the cyclic polycarbonates, really nice opportunities to engage in more sustainable chemistry, namely in replacing phosgene for manufacturing of polycarbonates and those performance materials. And so there's really great opportunities that come into play for additional sustainability by bringing CO2 in as the reactant rather than some of the traditional pathways for manufacturing these materials. And on the right-hand side, you see all the products and services from our performance hydrocarbon economy today. And the good news is we can recreate all of this from carbon dioxide. So let's look forward then. One of the key reactions to consider in this space is converting the CO2 into the synthesis gas by reaction with hydrogen. So you see up on the upper right-hand side, the reverse water gas shift reaction. And if you make synthesis gas, then this will be about the 4th time in our human history that we're looking at synthesis gas as a way to remake the hydrocarbon economy. This happened in the US back when I was young and doing coal gasification in the 70s, 80s. That was the only known resource we had, and we were looking at doing gasification and then Fischer-Tropsch and methanol synthesis to rebuild the economy there. It also happened in World War II and later with South Africa, where countries were embargoed and had only access to gasification as a conversion technology. Again, in the stranded gas era. So we built mega chemical plants now, which make synthetic lubricants out of stranded gas that have come into play via synthesis gas, and also performance alkane solvents for cooling of immersion cooling of data centers and such, and but also into the liquid fuels. And so now we're looking at a 4th era where we can use synthesis gas and grow these molecules and products by reaction of the CO2 with hydrogen often derived from water, in order to do this pathway. So all of this is well known and commercial at a high TRL level, except for the reverse water gas shift reaction itself, which is higher temperature than the forward water gas shift reaction that we currently use, and therefore is at about a TRL 7 to 8 phase. But once you have the synthesis gas, the rest of the steps are known at high TRL by Fischer-Tropsch, making acetic acid, or via methanol and derivatives, including pathways of methanol to olefins and chemical products, or methanol to gasoline, or methanol to plastics. We also have the opportunity, however, to skip this difficult equilibrium, which is high temperature, equilibrium constrained, and a challenge on the stability of the catalyst, and essentially do a direct hydrogenation. And we'll talk about the research agenda there. Currently about 50% yields, but by going directly into the hydrocarbon pathway, we look to pull this equilibrium to be able to make these products by Fischer-Tropsch, methanol, and then the methanol derivatives to chemistry. So those will be the 2 pathways that we're talking about today. Challenges in looking at these thermochemical CO2 conversion pathways. So one of the key ones is to work on that TRL 7+ reaction, which is the reverse water gas shift, by developing higher yielding and higher temperature and more stable catalysts. Improve some of the stereo and regio selectivity on direct use of CO2 and carboxylation reactions, and then develop processes that don't require stoichiometric reactants and alkylation agents, which are non-sustainable for some of these more specialty chemicals, pharma and food-related materials. Develop robust catalysts across all spaces that are inexpensive to use at an industrial scale and can handle impurities in the CO2. So we're going to be getting collections of CO2 at scale from pipelines and collected resources, and being able to handle impurities across multiple processes is going to be important here. Understanding of the carbon-carbon coupling to improve selectivity to long-chain hydrocarbons, coupling of different processes such as the reverse water gas shift and methanol synthesis, direct electrical heating, which we'll talk about in a little bit more as that opportunity from direct use of renewable energy and electricity and heating. And then the ability to incorporate CO2 directly into polymerizations that involve aromatic compounds. So we already have methanol to aromatics as a developed technology, but can we do some of that directly? The other platform areas in terms of processes, electrochemical, photochemical, and plasma chemical conversions are less developed, but have similar struggles in selectivity to specific C2+ products. And again, the carbon-carbon coupling reactions being a challenge, challenges in energy and atom efficiency, scaling of the electrochemical processes and devices, improved light and power management in the photochemical devices. So the LEDs are a big help there, but much further to go in terms of how do we operate these processes 24/7 and understand the fundamentals of the energy and mass transfer involved. Control of the selectivity of the plasma chemicals and the extremely reactive intermediates there, and work that's really at the beginning and fundamental discovery levels in terms of the TRLs for those particular processes. So in terms of research agendas, on the thermochemical, we're looking at improving catalytic activity and stability, sort of the common area in catalytic chemistry and conversion, but also incorporating the alternative heating. So where can we use electrical heating, either in a millisecond pulsing or in targeted heating of the catalysts themselves to improve the energy savings and improve selectivities beyond what we could do previously without that type of a heating approach. Continued R&D into low carbon hydrogen and in carbon neutral reductants. In terms of the integrated systems look at how do we integrate with high temperature reaction systems to incorporate the water gas shift and other reverse water gas shift and other reactions. Down here in the electrocatalysis, a lot of materials development needed to be done in that research space. So AI and machine learning for materials discovery for less over potential and more efficient platforms. And also looking at how to scale up and develop these modular technologies to deliver them at a low number up cost for the future commercial deployment. Membrane materials, a number of these reactions in these pathways are equilibrium constrained, and so integration of improved membranes can further improve yields in this space. The research agenda, continuing on for the photochemical and electrochemical and plasma. One of the opportunity space is to really understand the fundamentals across both of those processes in order to improve the devices and the selectivities enabled by those potential process routes. And then also this concept of the tandem conversions. And so you see from CO2, we have multiple reaction sequences to progress across, and looking at combining catalysts that can do that either in a single reactor or as a tandem catalyst, or consecutive and integrated reactor systems that can carry through these equilibrium and deliver at lower temperatures and higher yields and selectivities to the desired products. Integrated CO2 capture and conversion. Can you capture the CO2 and convert it on the same catalytic and integrate and get the cost savings there? And then we also mentioned the development of improved ways of doing the specific polymerization reactions directly from CO2, maybe not by going through methanol as an intermediate. So the good news is we can reconstruct the hydrocarbon economy from CO2 and water and the hydrogen derived from water. We've done this before using natural gas platforms, but we also have to consider how cost effective is it relative to use of bio-based feeds and or recycling some of the waste material in a circular economy will be the pathways that we'll be looking to optimize going forward. Growing carbon-carbon bonds from C1 molecule is capital intensive and can be expensive. And so we really need to value the climate and or synergistic ability to use renewable energy from around the world that may be available at high capacity factor and low cost in order to be building these molecules that can be then distributed globally and cost competitively in the economy, which is one of the attractive features to consider here. And so with that, I think I've used up my time, and I'll turn it over to Alyssa to speak about the alternative mineral carbonates at this point.
Thank you, Joe. Same as Joe, it's been really great pleasure for my side working with amazing colleagues in this area and led by Emily. Really, it was an intense but very interesting study in my opinion. And it's been really wonderful working with Joe and Jinwang and others. So this particular chapter I'm going to talk about is CO2 mineralization. And this particular area of research, especially R&D, started about 30 years ago in the United States, really looking at geological sequestration, how carbon mineralization is happening in situ. At the time, it was mostly on carbon storage and kind of understanding how even limestone is being made. That's a thermodynamically downhill reaction, as you know. It's like a basically acid-base reaction of silicon mineral, which is weak base, reacting with carbon dioxide, making thermodynamically stable solid product, inorganic solid product of carbonates, like a calcium carbonate, like limestone. But in geological sequestration, you can really make products, but we still learn a lot, and that was led by mostly geochemists. But about little over 20 years ago in the United States, chemical engineers like myself and others start looking into, can we really accelerate that reaction? Because in nature, although it's a thermodynamically downhill reaction, kinetic was limited, especially for magnesium silicate minerals like serpentine and olivine. And that was the reason it was limiting in terms of CO2 storage potential. As chemical engineers start looking at developing technologies and processes, perhaps we can do ex situ carbon mineralization, started with mine tailings at that time. And these mine tailings has high concentration of magnesium silicate minerals, which has really limited reaction kinetics and how to leach out and dissolve magnesium in solution phase, so that is limiting formation of inorganic carbonate solids. So in terms of process over last 20 years or so, we have direct carbonation reaction, indirect carbonation reaction, CO2 curing and injection leading to construction materials. These are the four main areas of in development many of us been working on. Recently, we even started looking into how can we use seawater to do mineralization. And a lot of these technologies are now merging between carbon mineralization and usage of a renewable energy, looking at electrocatalytic processes. So in this particular report, we were trying to tie where the feedstocks are, not only looking at the pure CO2 injected into geological formations, we are looking at a wide range of CO2 feedstock. Some are pure, some are not pure, different pressures and purities. And also looking at the much wider feedstock in terms of solids, whatever contains the calcium and magnesium and alkalinity. And looking at these processes more highly integrated ways. And in terms of third column, inorganic carbonate products, we looked at supplementary cementitious materials, CO2 cured concrete, precased concrete, as well as aggregates. And as I'm going to present a little bit, there are many interesting byproducts also impacts the techno-economic analysis of this overall process of these technologies. These applications are very interesting because, as Emily mentioned, this is one of the CO2 utilization pathways already at a commercial scale in some of these cases. We're looking at the durable carbon storage, both in situ and ex situ, but also looking at the construction materials, pulp and paper, pharmaceuticals, and agricultures. A lot of these inorganic carbonates can be lowering the carbon footprint of our product lines, especially the one with the much higher volume and weight. And once it goes into these products, more likely, unless you really increase the temperature at much higher temperatures, it will stay as it is. And because of that, this inorganic carbonates as solid products, we are looking at as long-term with the long-term carbon storage potential. So overall process itself, we are looking at how to, there are 5 main sections in this report. Carbonation of natural minerals and rocks. I'm going to talk about what are the challenges and research needs in the following slides. Carbonation of alkaline industrial waste and demolition waste, we are looking at all the way from the slags, fly ash, mine tailings, as well as looking into construction side of looking at the circular carbon economy in built environment, looking at recycled aggregates, reactive demolition waste, and so on. In terms of making construction materials, which is already far along in TRL, we are looking at CO2 injection and CO2 curing. And of course, already carbonated materials can be added into construction materials as well. So there are 2 additional areas of research, which is more recent development in around the world in terms of carbon mineralization. One of them is looking at how to electrochemically convert brine and seawater alkalinity into solid products through carbon mineralization. We did not look at or discuss the ocean alkalinity addition because we're looking at the products and also biological enhancement of that. We also looked at alternative cementitious materials and alternative mineralization pathways. And in terms of mineralization pathways in the past, most of research was only focusing on making maybe perhaps magnesium carbonate or calcium carbonate from various products. Now people are even looking at can we make something else containing carbon? For example, calcium and magnesium oxalate can have double the amount of carbon in these solid materials. So these are some of the alternative pathways we looked at. So challenges to overcome, how to get to mineralization going into the market and looking at the infrastructure as well. One of the challenges which been there from the beginning is the large energy requirement for mineral mining and processing. For example, if you're getting natural rocks and minerals that you have to grind them and mine them, grind them, and processing them. And these are the huge energy costs. And how to reduce that was a big challenges in this area. Of course, we need to think about environmental ecosystem impacts because the amount of minerals and water required for carbon mineralization for large CO2 utilization potential is really large. And also in this particular technology area, both reactant and products are solids, which means that transportation of these reactants and product will require a lot of energy and also infrastructure. So co-location we talked about earlier today is very important for this particular technology quite often. And as I mentioned earlier, mineral dissolution and carbonate rates are quite slow in the past. So how to chemically and biologically enhancing that rate's been really big challenge, but we made a lot of progress in this area as well. Third, we also need to worry about feedstock impurities. In the past, most of the research was done with very pure minerals and ores. But now looking at not only impure alkaline industrial waste and many other mineral inputs, but also CO2 and water, which may not be pure or high pressure. Finally, once you make products, although we have a wide product range now, in order for them to be deployed in the market, we need to somehow create the testing and certification of the materials produced by CO2 utilization. And that's very important, especially building materials. So here are some of the research agendas I'm going to present today. First, in order to really looking at the alkaline sources, the way not only looking at the minerals, magnesium, silicate minerals, and beyond, we need to look at the map of alkaline resources. One of the reasons is that not only we need to know where alkaline resources are, where CO2 sources are, because as I mentioned, transportation in between it could be challenged. So we are looking at we suggested that we should have multimodal optimization to really understand how to link in the infrastructure way, how to link the feedstock with the CO2 and even where the market is. And that will really involve the research on emerging approaches tying these together. The second one I want to mention is that ocean-based carbon utilization technologies. Recent years, many of us been looking into, some of you as well, how ocean alkalinity can be used to do carbon CO2 utilization and producing solid products. As you can see, bottom left figure, CO2, it has an equilibrium between atmospheric and then ocean CO2 storage. And because of that, we can harvest carbon out of the seawater and using the alkalinity in ocean as well. Many of these are slow, so that we have to use a strong acid and base quite often to accelerate the reactions. As you can see bottom right, looking at the different ways to add either acid or base to control that formation of solid carbonates from the seawater. But applying these technologies quite often challenged by local environmental changes and ecological impacts. So understanding that will be very important before we deploy these technologies in nature. And in order to really understand that, we are suggesting that we need to have a testing facility platform similar to National Carbon Capture Center, which is near the ocean with a wide range of environmental conditions so that many of the researchers and companies can test their technologies in the real life environment for the future. And then we also, as I mentioned, there's a lot of need for acid and base, and this technology has been done through electrolytic systems and R&D activities we need for electrochemically driven CO2 mineralization under a wide range of electrolyte conditions. One of the challenges we observed is that there could be membrane fouling issues due to the side reactions. Understanding these side reactions, including formation of chlorine, as well as the fouling issues, will be very important for the future. And finally, there are new alternative pathways really gained a lot of techno-economic benefits for these carbon mineralization technologies. As you can see in the bottom figure, people are now looking at calcium and magnesium bearing materials, either silicon minerals or industrial waste. Maybe there's some valuable elements like energy relevant critical minerals, for example, rare earth elements, lithium, nickel, cobalt, even copper. Can we develop chemical processes stepwise, extract as much as these valuable metals, at the same time maximize carbon storage potential? We can call it carbon negative mining. And in order to do that, there's a lot of challenges in terms of chemical dissolution as well as separation. And these separation challenges cannot be resolved or addressed without having strong industry, university, national lab collaborations. And we are highly encouraging that. Finally, it would be really important for us to start now, even looking at how to test and standardize and certify these materials so that we can deploy into the market quickly. And in order to do that, we need to have a lot of help in AI, machine learning, and other technologies to look at materials discovery and characterization. And now we're going to move to Jingwang Chen, who's going to be talking about the major findings of our report.
Hi, thank you. This is a graph. So both Jill and Elisa showed this similar full column graph showing basically you have feedstocks, processes, product classes, and also the product service. So this graph is the overall summary of everything we identified in this report. So the first one here, is on coal waste. But if from the CO2 perspective, the feedstock can be from two sources. It could either capture CO2 from air, right, or from concentrated sources, such as, for example, power plants or fermentation plants. The important thing about considering feedstocks is, especially if we consider CO2 footprint, we have to consider the other additional materials that need to be used to convert CO2. For example, as Jill mentioned, if you want to do thermochemical conversion, you need to use molecular hydrogen. And molecular hydrogen, unless it's from electrolysis, it can be CO2 intensive. And also, if you do thermochemical conversions, there's also heat that's involved. And if you do electrocatalysis, for example, then we need to use electricity or light. So from the process perspective, we need to do either physical separation, chemical conversion, also biological conversion, and hybrid processes that combines electro, photo, or thermochemical conversions, and also mineralization to make, for example, solid products. For product classes, we sort of divide them into three classes. The first one will be circular carbon materials. That could be the carbon-based material chemicals and fuels. But there's also the long duration storage materials, as what Lisa just mentioned. This could be inorganic carbonates. Polymers is one of another things that we can control with a long duration of carbon materials, and also elemental carbon. For example, solid carbon nanotubes, and carbon nanofibers. In terms of critical materials, this is primarily from the coal waste. For example, that can be rare earth elements and also some energy relevant materials. The important thing from this report is also we need to consider product service, right? What are the products that we need here? And also we need to have enhanced performance versus the existing products. It had to be durable carbon storage, decentralized production, and also we need to consider carbon material, the waste material cleanup. So it got stuck here. Let me try stop sharing and sharing again. For some reason, it was working perfectly during the practice. Let me try again. Share. Maybe try this one. Hopefully this will work. There we go. Yep. So overall, we have 71 research needs from this report, and they are by and large divided into 3 categories. The first is reaction level understanding, second one system level understanding, and the other one is really demonstration and deployment. So I will not go into too much details. They're all here. Just pick a couple examples. If we do reaction level understanding, we need to know fundamental knowledge and also, for example, catalyst innovation and optimization. If we think about system level understanding, we need to consider energy efficiency, electrification, and also alternative heating system, just as one of the examples. And if we think about demonstration level, for example, enabling technology infrastructure would be very critical. So all those details are in the reports, and you're welcome to read them. And also, based on those research needs, we provided guidance, including the funding agency, including which particular research needs can be funded by DOE, for example, or other federal funding agencies, industry, and also the research community can really focus on to improve CO2 and coal waste utilization. So the overall summary from the report, we will have 4 summaries. The first one is based on the analysis by the team. And what we conclude is that CO2 utilization can provide circular carbon products and also durable storage and achieve a net zero future. The second one is really critical, is we have to really apply technology assessments. They are essential to realize the benefits of CO2 utilization. And the third one is related to infrastructure. So we need to have integrated infrastructure planning, and then they need to balance cost, safety, environmental impacts, and also prioritize public engagement. And finally, that's related to research. We need to perform both basic and applied research, and we also need to demonstrate this research in a large scale and also enabling technology developments. Those are all together are required to achieve CO2 utilization, CO2 conversion, and also coal waste utilization. So again, details are in those charts. And then finally, I just thank you for all your attention here. If you're interested in reading these reports, here's where you can get the report. So now I think we just open for questions. You can use the Q&A button, and Jean would read out the questions.
Yes. Okay. Thank you for the presentation. I have a bunch of questions. First one from Jeff Levintz. Isn't outsourcing of manufacturing from the U.S. to other countries, especially China, a factor in the moderation of CO2 emissions from the U.S.? And Joe, you indicated you wanted to answer this question.
Yeah, so it can make us look good where we've exported some of those emissions, unless you look at scope 3. And so, but yeah, certainly it's a global climate problem. But you have to keep in mind, in terms of these chemical products, the U.S. is a world leader. It's one of our top manufacturing industries in terms of the economic value to the U.S. economy. We're a leader in the space. We've developed a lot of the technology. And so I think it's important for the U.S. To maintain that leadership role. A lot of that goes with low-cost energy. And so having the capability of pulling the CO2 platform into our process technology to continue to deliver those exports and the value to the U.S. economy, I think is going to be very important going forward.
Okay, the next one is more a comment, but maybe we can comment on it from Steve Lewis. We need immobilized carbonic anhydrase for CO2 mineralization at bioethanol plants. Need research funding. And Alyssa, you wanted to address this?
Yeah, so carbonic anhydrase, if you're not familiar with, is an enzymatic catalyst. Both humans, animals, plants, all of us have it because it's critical to accelerate the hydration of CO2 and also reverse reaction. So even earlier time on carbon capture technology research, R&D, carbon and carbonic anhydrous have been looked at. So I remember one of the first major research funding given to this technology was 2009 by ARPA-E impact program. There were smaller startups did really good job. And I think earlier time carbonic anhydrous, you can purchase it, but it was very expensive because they were usually getting it from cow's blood and then purifying it to the point that it was very expensive. But like a detergent, they were able to reduce the cost quite a bit. So they actually developed carbonic anhydrous solution for carbon capture material solvent system. Now, looking at the immobilization of carbonic anhydrous, allowing us to do a lot more robust integration of this material, enzymatic catalyst for various application areas, including CO2 mineralization. Because in earlier time, CO2 mineralization, there are two steps, mineral dissolution and solid carbonate formation. The mineral dissolution was the limiting factor, but once we accelerated that, even hydration of CO2 was holding it back. So now people are looking to immobilize carbonic anhydrase to enhance that rate. And I think there are many applications we can have in immobilized carbonic anhydrase.
Okay, next question from Jeff Luventz. Is there a role for nuclear energy to enable CO2 reduction to useful organic fuels, chemical, and polymers? And Joe, you wanted to take this one on?
Yes, and the answer is most certainly, Jeff. So these complexes to convert CO2 into these chemical and fuels products are capital intensive. They need to run 24/7 and also often involve the need for high temperature process heat. So incorporating nuclear with a very high capacity factor and the ability to provide that heat is really an excellent enabler for this. So by all means, bring on the nuclear. We'll be looking at that as an option.
Okay, question from Margaret Wu. Why ignore photo conversion of CO2 or plant-based CO2 conversion process? Joe?
And we didn't. And yeah, go ahead, Emily.
I can just say that biological processes involving plants were out of scope for this report. We did look at biological conversion. There's a whole chapter on biological conversion. We didn't emphasize that in the presentation, but you're welcome to go peruse that.
All righty, and that's correct. And you can combine the two. So we can combine the thermochemical with a feed-in for some of the bioconversion, such as the Lonzatec fermentation technology. And so we've looked at that. And yes, I went quickly, but photo conversion is part of our research interest. It's a little bit less developed than the electrochemical and the thermocatalytic, but certainly it offers great potential, especially in co-converting water and CO2. And so it's on our research agenda in terms of how to get the light into those reactive systems and then address the fundamentals needed to make that go into the more feasible space for further development. So it's in scope.
Yeah, photo.
Okay, I have a question from Craig Benson, who is asking, we have been engaged in harvesting and processing historically disposed coal combustion residuals for use as supplemental cementitious material, SCMs, that replace Portland cement and concrete. This has a very favorable reduction in greenhouse gas associated with producing concrete for infrastructure while also improving the engineering properties of concrete. Would the application described today be superior to the use as SCMs?
So I can answer that question. So of course, one of the areas people have been looking into these materials is SCMs. It's historically people been using fly ash as SCM as it is. But I think in recent years, including the technologies we present today, is the how to make better SCMs, and then how to even extract out other impurities as a valuable byproducts. And I think that's where we were. So we didn't really go into detail on the chapter on coal waste, but even not only coal waste, other industrial waste, steel, slag, and many other things, we can make it into SCM. But the way we can do it is if it is already good SCMs, you can use it directly. But if there is a valuable other materials, and if you have a less effective SEMs, then we can actually chemically process them. It was economic enough for us to separate out different elements and then put it into SEMs, or even as a construction materials, or even making concrete itself, like a Portland cement. So those are the approaches we've shown. I think this report will show that what are the chemical pathways and how to integrate these systems with different electrochemical and thermochemical and these pathways to maximize the usage of all these solid materials, at the same time minimize any waste generation. So you will learn a lot about other options in this report.
And just to add to that, the chapter, thank you, Alyssa, that was terrific. So if the chapter on coal waste utilization, points out that it's all this, they are being used, of course, already as supplementary cementitious materials, and it is that's the low-hanging fruit, right? And then when you think about using them then to actually make concrete, that's more where the CO2 is going to come in terms of making the aggregates that make up the overall composite that is concrete.
Sort of a related question that's coming up next from James R. Has anyone questioned the wisdom of turning our atmosphere into rocks?
Okay, I'll take that. I mean, we're not talking about converting the entire atmosphere. We're talking about taking excess CO2 that's in the atmosphere that is warming the planet and taking that component and turning it into rocks, or at least not exactly rocks, but useful minerals that can either just be stored so that they don't warm the earth, or can be utilized. And that's what this report is about, is not just storing, but utilization of such minerals.
Okay, next question from Haikon Timken. How about sequestrating CO2 in the reservoir without conversion? Since the CO2 conversion is expensive, would sequestration as is be more cost efficient?
So, of course, that is being considered, and the issue is the daunting, and it is extremely likely that we will be doing that in addition to CO2 utilization. And in fact, the amount of CO2 utilization that we can do is not going to be enough to take out the carbon dioxide that needs to be removed from the atmosphere. So they'll both be done. They're both not cheap at this point, right? And these are technologies that are still under development, and there's still issues with respect to where we will do them. For example, Europe has voted with their feet that the only CCS that will be done will be offshore, and that makes it more expensive, but presumably safer. And so it has not yet been decided in the US where and whether we will do it.
And in this particular report, we talk about how infrastructure build out will be different for CCS versus CCU. And because of that, we actually had, remember that feedstock I was talking to you about, the alkaline source. There are a wide range of industries, including steel plants and power plants and cement plants and so on. And that infrastructure discussion on utilization versus storage makes a big difference as well. And that has been discussed in this report.
And it does take less energy to store versus capture to make the hydrocarbon products. And so we did emphasize that in the first report to look at the systems analysis and where you want to spend your energy, and certainly consider storing, and then consider what the CC utilization opportunity would be. But there aren't really good sinks everywhere in the world for storage. And so having some of the utilization also is an enabler for those portions of the world where we don't have it. Fortunately, in the US, we do have the sinks available.
Okay, I will just add that Jeff Levins just provided a comment to this question that Archer Daniels Midland has been sequestering CO2 for more than 10 years so far, 4.5 million tons. Okay, the next question from
I will
Eva.
say that has been going on in actually multiple places. It's just not being done at the scales that would be necessary. That's true.
Right, we have it in multiple places in Canada and the US. And bottom line is we've been CO2 capture and storage ready, but the will and money to do that capture has not been present in order to go beyond the demonstrations. And so that's
Exactly.
what we're looking to tackle now.
Okay, next question from Eva Lerner Lamb. Do any of the researcher have a back of the envelope assessment and recommendation for CO2 recaptured processes for roadway pavement purposes? Are there obvious advantages or disadvantages of considering such processes?
So it goes to the carbon mineralization technology, and people did look at it somewhat, but not as much because there are other feedstocks people are very interested in, including the alkaline industrial waste and natural ore. Roadway pavement is one of the applications people like to put solid carbonates, aggregates, because compared to building materials, building really high buildings, tall buildings, which you need requires a specific certification and mechanical strength and all that so on. Roadway pavement is much easier material to make. And you can hide a lot of carbon and store a lot of carbon in there. So as an application, we've done a lot. But going back to the same way that if you're trying to recover roadway after the end of its life, and then where to transfer it to and how to convert and then putting it back into the roadway, there's a lot of infrastructure discussions we need to have. We didn't have a lot of discussion in this particular report because the fraction of it may not be as big, but this will be one of the areas. Because in terms of solid carbonate and carbon cycling that in built environment will be a big discussion, and all of those will be discussed in the future, I'm sure.
Okay, here's the question from Julie Cornfield. Anthropogenic greenhouse gas emissions to increase, and current carbon capture is at 1/1000th of current emissions. Quantitatively, what greenhouse gas emission would be required to implement a 1000x increase in the infrastructure for carbon capture and use? In a world that is far from net zero energy, what rate of ongoing greenhouse gas emission will result from operating these at 1000x greater scale?
Well, I'm not sure exactly what's being asked here, but the carbon capture storage can potentially address up to about 18% of the global emissions. And again, it needs to be incentivized because it is an added cost. But all of these mechanisms really have a levelized cost of CO2 emission mitigation. And if the situation is beyond the announced policies, we have very little that are in place really globally to do a significant reduction in greenhouse gas emissions. We have the stated pledges, which are non-binding, which take us further, but we need to have more of that of the policy in place really to be able to expand at that type of a rate. And then we get to the interesting game of deciding of do we store it, do we utilize it, and how best to go about it.
Yeah, I
Okay.
think it's important to the question was, I think, I'm not sure that all of us completely understood the question, but I think that it's important to recognize that there are multiple paths that have to be taken. So there's both decarbonization to reduce emissions, and then there is, what are we going to do with the historical emissions and the ongoing processes that continue to produce emissions. And so all of those and then do we store, do we utilize? And Joe mentioned, what we might be able to do in terms of emissions with respect to storage. The thought is based on current emissions that we might be able by 2050, and the reports talk about this, store, a few gigatons of CO2 emissions used as utilization. Okay. So it's not going to solve the problem by itself. And so, it's not enough to just talk about CO2 utilization. It's clear that this is part of what has to happen because we still will have a carbon-based future, but it's a part of the puzzle. And the rest of it has to come from decarbonization of our electricity and our whole energy system. But but it also then has to come with transformation of everything in society to not be continuing to emit, and with carbon dioxide storage as well. That's going to have to be not just through utilization, but through sequestration, geological sequestration. So all of these things have to happen at the same time in the next 25 years.
Okay, here's a question from Rangarajan Ramesh. How about CO2 to urea using catalysts?
CO2 is already made. I mean, urea is one of the main products that uses CO2 right now.
Okay. Question from Yushan Yang for direct air capture and DOC, direct oxygen capture?
Ocean capture.
Oh, direct ocean versus point source capture. DAC, DOC does not have an alternative, while point source can be avoided by adopting clean source of energy. Should we prioritize avoiding point source emission over capturing it afterwards?
Yes,
Joe.
and we're doing that. The mantra is electrification first, but certainly not all sectors of the economy are readily amenable to that, and especially a lot in the industrial sector. So basically, and then we have the existing asset base. And so the pathway to decarbonization involves a great deal of CO2 capture in addition to the other mitigation strategies that Emily had previously mentioned.
I think it's also important, and Joe was alluding to this, that we are going to be undergoing a transition, and that transition will start by capturing CO2 from point sources, because the point sources aren't going away soon, as was pointed out by Joe, in terms of the assets that are already there. And we can learn a lot by testing our capture and conversion approaches on those kinds of point sources. But ultimately, those point sources will go away, and we have to be factoring that in to the investments, understanding that stranded assets are a concern. And so all of that has to be factored in as we build out these technologies.
And that is the driver for the direct air capture facilities. It's a bit more expensive, but you have the long-term viability of that as a source, and then the low carbon emissions that go with the products made.
And it's clear there's a lot of challenges still with direct air capture. There's a lot, they're exceedingly expensive, they're energy intensive. So there's a lot of R&D that has to be done. But, there's a lot of creative people working on both direct air capture and direct ocean capture, so that ultimately that's going to have to be part of this, a large part of the solution.
Yeah, initially people thought that point source capture will be deployed first. And in fact, we work really hard to do that. Or even as the question mentioned, how to clean our power sector so that we don't need to do CCS. I mean, we have to do both in the transition time for sure, for decades to come. But direct air capture and direct ocean caps less so, because it's more emerging technology that both of them kind of picked up much faster because of infrastructure issues, which we discussed in this report, because they thought that direct air capture DAC and DOC can be installed at the either utilization site or storage site directly without having pipeline. Whether it's always true, it's not always true, but close to many of the cases. And I think because of that, utilization and storage companies wanted to deploy DAC or DOC in their site. And because of that, you see a lot more demonstration. And also DAC and DOC being developed as a modular design. So instead of scale up, usually scale out. So they can start with a very smaller version of demonstration and then add them together. So it's kind of interesting way of engineers, like chemical engineers, looking at how to deploy such technology. But at the end of the day, the biggest climate change impact will be point source in near term, because at the scale we're going to be building. But I think we can learn so much from both point source as well as the distributed sources.
Okay, a question from Kevin Anderson. Many of our NAE members from industry review and sign off on the materials specified on engineering prints. Is there a vetted list of net zero polymers that are in production with corporate contact information? Many of our members can help drive industrial market demand by specifying these materials in consumer products. Joe, did you want to answer that one?
Yeah, and I think the answer is no, we don't have a formal NAE vetted list in that space, but that would really emphasize the need for a life cycle assessment and then the vetting of the methodologies used there in terms of how do you do that. And so that is something that is in development from Argonne and the GREET model and elsewhere. And I would say that on the average, there's more of that happening in the fuel space, such as for synthetic aviation fuel, where there are blockchain procurement mechanisms that help link those entities together. But it hasn't really gone into the polymer space quite as quickly as it has for the fuels, because fuels is a bigger target. It's 10x higher than the chemicals emissions. But that is something that could be done and would help get the vetting in place that's necessary to really show what those benefits are. I think a number of the companies advertise on their own in that space, but the vetting, I think, is very important to compare the assessments.
Okay. I have a question from Henry Kister. This may be outside the scope of this panel, but one technique that I have not seen addressed on decarbonization agenda is to improve processes, flow sheet equipment, operations, and diagnostics. Am I missing something? Is there anything done along these lines? Joe, you.
Yeah, that's always the low-hanging fruit. And I would say with AI and machine learning, we're really able to drive another phase of bringing in. So how do you get some of those efficiency gains and then bring in some of the new toolkits to do that? So I think AI and ML are really driving a new era there that we can look to further make improvements. I think the IEA estimates maybe 8% or so further improvement in that space that can be done on the manufacturing side.
I think
Question from Susan Brantley. Oh, sorry. Go ahead, Alyssa.
I think it's an important question for anything we presented today, because all the technologies we talked about is a wide range of feedstock, how to transfer them, how to react them, how to separate them, and how to put it into market. And looking at all these efficiency issues and how to integrate the materials and energy and minimizing waste, all these impacts on TEA and LCA. So I think it is a sprinkle through or discussion through entire report. And I think these are the key things we need to improve for the future.
Well, I would say they're one of many things we need to do.
Yes.
It's certainly the case that we emphasize that in the technology assessments chapter, the need to think about systems integration and to analyze all, cradle to grave, how to optimize these processes. It's a new era, right? The petroleum industry has had many decades head start, and so there's just a lot more to do. On the other hand, I think it's extremely important that we recognize we have a lot we can learn and leverage from the petroleum industry for all of this kind of work. Gene.
Yes. So I have a question from Susan Brantley. Some people suggest that we mine, grind, transport, and amend soils with basalt to enhance weathering. For example, to accelerate the rate that silicate rock reacts with CO2 and water to draw CO2 out of the atmosphere. Was this considered in the report as a viable opportunity for negative CO2 emission technology, or is not considered to have much potential?
Well, I'm sure Alyssa will say more, but it definitely is mentioned in the report.
It was mentioned in the report, but as I can tell you that basalt, compared to the minerals I talked about, serpentine and olivine, the amount of alkalinity is much lower. So calcium and magnesium content is lower. So quite often in the past, basalt was considered for in situ mineralization in geological sequestration. And most of the pure minerals with the highest concentration of calcium and magnesium, it's totally worthwhile to mine and grind and transport and work with it, especially, for example, olivine and serpentine are actually mined significant mountains each day for nickel recovery. And because of that, nickel content is only 0.2%. So we had a ground up serpentine and olivine as mine tailings, and that's where carbon mineralization started quite a bit. And naturally, it was absorbing CO2 from atmosphere as enhanced weathering naturally in the mine tailings. Now, the technologies we presented in this report are accelerating that rates. Whether basalt can be used to directly capture CO2 from atmosphere, maybe it's even slower than the serpentine and olivine, but the reason a lot of us are interested in basalt in this field is that we have a lot more of basalt everywhere. It's really abundant material, so that having that as more passive, like direct air capture technology has been considered because of the availability of these materials in many different locations.
Okay, question from Alex Urban. CO2 capture from point sources can only account for less than 20% of global emission, and it must be incentivized globally, for example, through a global carbon tax. Considering that point sources will eventually disappear, are we spending our limited resources wisely by investing in carbon capture research? Or would it be more effective to prioritize the accelerated development of zero carbon processes and the climate resilience of infrastructure? So Emily, I think you wanted to answer this one.
Yeah, it goes back to what I said before. No one set of solutions is going to work. And so we are already at a stage where we not only have to worry about climate resilience and climate adaptation, that's got to be a train leaving the station, but it also is the case that, and of course we have to be prioritizing what you're referring to as zero carbon processes. I think you're referring really to zero carbon energy, electricity in particular. And certainly that has to happen. But we have the small problem of the fact that we have emitted a tremendous amount of CO2 into the atmosphere, continue to do so, and will continue for certain kinds of activities. It is extremely likely that we are not going to come up with, and there's many analyses that agree with this, we're not going to have heavy-duty transportation, such as long-haul aircraft and heavy shipping, doing anything other than using hydrocarbons as their fuels. And as a result, there's going to be CO2 emissions for the foreseeable future. And so we have to both clean up the century and a half of legacy emissions to the atmosphere, which will take a long time and therefore needs tremendous investment. But we also have to recognize that there's an ongoing amount of CO2 that's going to have to be captured because of various human activities that will give rise to continued CO2 emissions that will still potentially be harmful. So for all of those reasons, we have to continue to invest in CO2 capture. And the CO2 capture, as I said, I think we have to invest in both CO2 capture that works for taking it from the ambient atmosphere as well as the ambient ocean, but also from point sources, because the point sources are going to be with us for quite some time until we stop using steel plants, cement plants, and power plants, among others. And that's just that, at least being, let me say, conventionally produced, then we're going to need these technologies for decades to come, at least through this century.
And I think we also need the negative emissions. So direct air capture with storage, carbon dioxide reduction, CDR, is really going to be important for dealing with the offset in terms of legacy emissions as we're going forward. So a very important area to continue to study.
Carbon dioxide removal, CDR. Yeah. Yeah.
Okay. Question from Margaret Wu. Should we explore using higher CO2 concentration to promote faster or higher food production in greenhouse?
Actually,
and we've done that.
Done. Yeah.
We've captured EO off of our chemical processes in Europe and soon in the US and done that, and it grows lovely tomatoes. So, but we can't solve the world's problem with that.
Yeah, that's I think really important point. So it is already being done in demonstrations of actually direct air capture, for example. There are off-takers for, greenhouse off-takers, but it's a very tiny amount of CO2 that is needed for that. So it's not, it won't take care of the CO2. And it also, if it goes to create tomatoes, et cetera, that's at best circular, right? Isn't taking care of, eventually that CO2 is going back to the atmosphere.
Okay, have a comment from Eva Lerner Lamb as a follow-up to my previous question. CO2 weed capture material for roadway pavement. I agree that the long-term life of CO2 should be factored into an analysis of how well the material performed from a net zero perspective. But I think it is also important to conduct a comparative analysis of those CO2 recapture materials against the current blacktop asphalt pavement processes. I believe the latter would generate substantially greater excess CO2 emissions. Any comment from our panelists?
Agree completely. Do the LCA, and that's what we preach in the report. Is you really got to get serious with those numbers, and it's a systems by system look at those comparisons to make the right choices.
And the performance matters, as you kind of mentioned in the question itself. So then let's say we made a new material to replace the carbon intense building materials or construction materials like this. Let's say there is a lot different lifetime of this pavement change, or even the abrasion of the tire from the car changes. There's so many environmental impact you can change in the long-term lifetime of this long-lived product. So when you try to understand the performance and certification and all that of the new products to replace the current one, you need to think about not only performance, but also lifetime, the environmental impact of all these technologies. And then that will be very important.
Okay, I think there's just one outstanding question left. It's from Jeff Levins. Is there something useful that could be learned and applied from natural formation of seashells?
Well, that's happening. I mean, seashells, it involves calcium carbonate. And so certainly that's true. But it's happening at a much, not at a fast pace, let me say that. But certainly, yes. I mean, that is a natural formation of calcium carbonate.
I think we have answered every question and comment.
I think Tom and I would really like to thank the three speakers, Elisa, Jill, and Emily, for answering all those questions. But we also want to point out that today's talks are primarily focused on chemical conversion and also mineralization. There are many, many aspects, right, such as biological conversion, life cycle analysis, and infrastructure. They're all in the reports as pointed out by Emily. So Emily, do you have any overall summary statement? Yeah.
Sure. I think that the report is a fountain of a tremendous amount of information, both the final report, but also the initial report, which I don't think I mentioned, but it was done on a fast track, meant to be delivered within a year in order to help inform the decisions that were being made by the federal government at the time in terms of infrastructure investments associated with CO2 capture, utilization, and storage. So that report I think is still useful if such projects were to go forward. The second report, I believe, is especially the research agenda, but all of it. I mean, there are many different components to it, but the research agenda, especially potentially for many people who are listening, is something that will be long lasting. I believe that this report should be useful far into the future because it's really calling out what are the challenges ahead, being very clear that this is not a panacea, but that it definitely has a place as part of the solutions ahead for life on the planet to continue long after we are all gone. So with that,
Thank you.
I'll stop.
This is Tom. I'll just add, I wanted to thank all four panelists for an excellent presentation. The reports are available through the National Academy of Press, free download. You can download the chapters or the complete reports. A copy of this webinar will be posted on section 3 on the section 3 website on the members website if they're available. Gene, any further comments?
Yeah, I just want to say on behalf of the chemical engineering section of NAE, I want to thank everyone who joined today's important conversation on the future of CO2 utilization. I'm very grateful to our distinguished speakers for sharing your insights and ideas that we hope will inspire both innovation and action. We hope this is also the beginning of continued engagement across the engineering community to address climate challenge with creativity and impact. So just want to thank everyone for participating, all our people who presented, the people who attended, and people who asked questions. And certainly we can continue this conversation as we can connect with each other.
Okay.
I want to thank you all from the NAE for organizing this. And I hope that, and I appreciate all the people who stayed on listening to this important conversation.
Okay.
So with that, I think we can close the webinar.